Today we're going to start Chapter 5, Day 1. What we're doing today is we're going to be looking at exponential functions, their graphs, and then solving some equations with variables in the exponent. Now, you guys have done some of this stuff before in Algebra 2, so what we're going to do is on this front page, reading the directions, use your graphing calculator. So this is all in the calculator. Create a sketch of the graph, then determine the y-intercept, the asymptote, the domain, and the range. Now remember, for all exponential functions, there's a horizontal asymptote. So what I want you to do now is pause the video, go ahead and complete all 9 of these on your own. You're just going to type each one into the calculator as y equals, and then I would recommend using the table second graph on your calculator, the table setting, to find preferably three really nice points and plot those accurately on your graph, and then go ahead and unpause the video once you've finished all 9 of them, and check to make sure that your graph is correct, but also make sure that you found the correct y-intercept, asymptotes, and then the domain and range. And then we'll go ahead and talk about that and move on to the back page. All right. So what we're going to do now is we're going to go through each one just to make sure that you got them right. So for number 1, we have f of x equals 2 to the x. When you type that in your calculator, I got that table on the left side. The 3 nice points that I took were 0, 1. That was a great point. It's also our y-intercept, so we can label that 1, 2, and then 2, 4. We labeled those 3 points. In this case, it was exponential growth, so it worked upwards. And we know that because exponential graphs go left and right forever, our domain is from -infinity to infinity, and our horizontal asymptote was y equals 0, because that graph will not go anywhere below that x-axis. So therefore our range is from 0, but not including 0, up to positive infinity. Moving over to number 2, we take a look. This graph moved up. So we have the y-intercept. If you plugged in 0 for x, you would get 2 to the 0, which is 1 plus 6. Your y-intercept is at 0, 7. The horizontal asymptote moved up as well. It's at y equals 6. And then again, the domain is always going to be -infinity to positive infinity for all exponential functions because it goes left and right forever. But this time, our range is from 6 to infinity because that's where our horizontal asymptote is. If we take a look at number 3, this graph had reflected, there we go. This graph had reflected downward. So this time our y-intercept is actually at 0, -1. And then the horizontal asymptote is still on the y equals 0 line. Domain's the same. And then the range is from -infinity to 0. Make sure, again, we are from least to greatest. It goes down forever, but it cannot pass that y equals 0, the x-axis. There's our table. And then moving down, 5, 6, 7. Again, you just plug these into the calculator for now on this practice. We got a lot going on number 6, so just be careful. Make sure you type it in properly. Use the parentheses where they're supposed to be applied. And then just double check these 3 real quick. And then moving down to 7, 8, 9. Again, we notice that the base, we use 2 as the base for all of our exponential functions above. But for 7, 8, 9, we just changed the base around. So we notice that the graphs are slightly different. But again, they're all exponential growth or decay. Just a change of the y-intercept, maybe the steepness of that exponential function, and then the range as well, and the horizontal asymptotes. Okay. So that was just using your calculator. Make sure we have that ability to type it in, find the table, and plot specific points. That's going to be helpful not only this year when we are able to use the calculator, but also moving forward in your Calc AB or BC class next year, and then into whatever future math classes you use. But what we want to talk about now is on the back side. I already kind of wrote these out for you. So again, if yours is blank up top, if you want to pause it and write these down. But basically what we did on the front, and we'll go back and show you the example that we did with the base being 2, but we were applying reflections and translations to an exponential function. Okay, so the base function was y equals b to the x. In our example, it was, we can even use f of x. In the example, it was f of x equals 2 to the x. So I'm going to go back and forth here a little bit, but this was our base function, right? So this is the first one. And then from there, you guys have done transformations before in the past with square root functions, quadratic functions, linear functions, all that good stuff. Now we were just applying different transformations to our exponential function. So the same rules apply, they're just in different spaces. So for this one, the a value, which is in front, if there is an a value in front being multiplied by your base, that's going to represent your y-intercept if the h and k are 0, because, not to jump ahead here, but h and k are going to be your translations. So obviously if you move it and you shift it up, down, left, or right, then your y-intercept can move as well. But if those are not happening, then you can take a shortcut and make a your y-intercept. Just keep in mind as well, because we talked a, normally that if it's in front of a square root function or a quadratic function, if a is negative, that's a vertical reflection. Okay. B, which is the base, you can use different colors here. B, which is the base here of your exponential function, that's the 2. If it's greater than 1, then we have an exponential growth. And if it's between 0 and 1, then we have an exponential decay. Okay. Now keep in mind though that this only applies if that a value is not negative, right? Because if I have y equals 2 to the x, and we can look at this back on the front side, if we have, for number 3 here, our initial function was y equals, or f of x equals 2 to the x. Well, our b value is positive, so we would think that it would be exponential growth, but again, we know that because that a value is negative, it actually ends up being an exponential decay. So when you graph these using transformations, you first want to look at the b value to see if the initial is exponential growth or decay, and then you need to look at the a value in front to see if it's going to reflect it over the x-axis or not. And then for C, we don't do a lot of horizontal stretching in our exponential functions, but if this is a number larger than 1, it would be a horizontal compression, and if it's a number between 0 and 1, it would be a horizontal stretch. But mostly what we'll see is if that C value is a -1, then it's going to be a horizontal reflection. And then finally, let's see if I have another color here. Finally, use gray. The H value and the K values are your translations, right? So just like when we did our square root functions and our quadratic functions, opposite inside, exact outside, if we look back at let's take a look at number 9. Let's take a look at number 6, just because we still have that base. We got a lot going on in number 6. So again, the b value was positive, but the a value here is -1. So instead of a exponential growth, that has to be an exponential decay, which would look like this. But our graph doesn't look like that because we also have a horizontal reflection. So we got a lot going on here, which is why it ends up being that shape there. We have a vertical reflection and a horizontal reflection, but then even more after that, we ended up taking that graph that was reflected 2 ways, and we shifted it right. So we went from here, this was the y equals 2x, 2 to the x graph, right? We flipped it over the x-axis, and then we flipped it over the y-axis. There's a lot going on here, but hang with me. And then we took this function right here, after we reflected it twice, and we shifted it to the right 4 units and then up 6 units. And that was our translations, which is how we ended up getting that. Now, you did that on the calculator, but in this class, we got to make sure we can do things without a calculator, because moving forward into Calc A, B, and BC, you're going to be asked to do things without a calculator, and we will also be asking you to do things in this class without a calculator, so make sure that we're good on our transformations. So that's the graphs. We did it all on the front side. Again, we've done that before, so in the homework, it's going to ask you to do some transformations without a calculator, so please make sure you follow those without a calculator. Just keep in mind, just like you follow the PEMDAS rules, you're not going to do addition subtraction first, because that's out of order. We first have to look at the growth or decay, the b value, and draw the general sketch for the seed, the base function. Draw that first one, maybe as a dashed line, and then go ahead and follow your reflections, and then go ahead and apply your translations. So for the homework, that's what you're going to be doing for graphing. Moving down to the second half of what we're doing today, we're just looking back at our our exponent rules. So we have to remember these from Algebra 2. Remember, this is a power to power. So right here, if I have a base, which is the square root of 2, being raised to the square root of 2 raised to the square root of 2, if I have a power to power rule, I'm going to multiply those two values. That's the exponent property for power to power. So square root of 2 times square root of 2 is square root of 4, which is just 2. But then remember, you can either cancel those out, or square root of 2 is 2 to the 1/2 raised to the 2. Again, you can multiply those. You get 2 to the first, which is just 2. Moving on to the next one. So that was the power to power rule. This one, you're multiplying two numbers that have the same base. Well, if I'm multiplying two numbers that have the same base, if you remember, we can add their exponents. You are not multiplying the exponents. That was the power to power. For matching base, when you are multiplying those bases, you add the exponents. So if we do that, we notice these cancel out. That ends up being 4 squared, which is 16. And then finally, this one again just uses the power to power and simplifying. So we can go ahead and say 3 to the square root, or square root of 3 is 3 to the 1/2. So we can say 3 to the 1/2 times pi. So we're just replacing the square root as a 1/2, all raised to the 4th. And then again, going back to our power to power, we know that's 3 to the 4 times pi over 2. That would be 2 over pi. 2 pi. 3 to the 2 pi. That pi is in the numerator. So with that quick review of your exponent rules, make sure you know those. We're going to go ahead and use those to solve some exponential equations. We also did this back in Algebra 2. If two sides of an equation can be rewritten with the same base, it'll make it a lot easier to solve. We're going to talk about logarithms later in this chapter, but if you can rewrite this same equation without changing the numbers, with just changing the way they look, and they have the same base, then it'll make it a lot easier. So what we want to do here is we want to get both sides to have the same base. Well, 27 on the right side can be rewritten as a base 3, but I can't just change the number 27 to be 3. I have to write it as the same value. So 27 is equal to 3 to the 3rd. So again, all we did was we said 27 is 3 to the 3rd. So we replaced that number. But now by doing that, I have matching bases. So because we have matching bases, we can say 3 to the x equals 3 to the 3rd. Well, since the bases match, we can say that their exponents match. And in this case, we don't have to do any more solving. It's already done for us. And again, you can always check by plugging it back in. Is 3 to the 3rd equal to 27? Well, yeah, it is. So go ahead and pause the video for a minute. Try number 14 on your own, then unpause the video and make sure you got it right. All right, checking out number 14. Again, in this case, you cannot change 27 to be a base 9, so you got to change both sides of the equation. So the left side, we changed 9 to equal. 9 is equal to 3 squared, but we cannot ignore that t because it is in the exponent. So we have 3 squared raised to the t. All we did was we replaced the 9 with a 3 squared. But we kept that t. And then again, we talked about power to power. So that left side is equal to 3 to the 2t because we're multiplying exponents. And then on the right side, we already said 27 was 3 to the third. And again, once we have those matching bases, we can set the exponents equal and finish solving that equation. For number 15, we're going to go ahead and do the same thing. Again, just following the concept of matching the bases. So what we're going to do is we're going to look at the right side, and we know a square root is a 1/2 exponent. And by changing that, we now have the bases matching. And again, we remember when the bases match, we can go ahead and set the exponents equal. By doing that, you get 1/2 equals 2y, and y equals 1/4. If you plugged it back in, it would work. So for number 16, go ahead and try this one on your own. Pause the video and try it, and then go ahead and unpause it after you're done. Check your work, make sure you got it right. There's the work. On the right side, we have a little bit more to do. You have to change 2 numbers on the right side to get the same base, and then we needed to use the addition or the product property where the bases match, and you can add the exponents. So then we have a singular base, and it's only then that we can set the 2 exponents equal to each other. When you do that, you get 5/2, and it does work. Last 2 down here. We're solving just a bigger equation. It looks complicated, but if we just think about it as if it were just a normal polynomial equation, it's pretty straightforward. We have 0 by itself, and we can factor out a GCF of 2 to the x, which is really nice, because then, now that it's factored, you can factor it one more time on the inside if you want, because it's a difference of squares. But I'm just going to leave it there for now. Because it's factored, we can set each factor to 0 just as if we would any other time. So 2 to the x equals 0. 4x squared minus 9 equals 0. And then we can go ahead and solve for each variable. The tricky part on this is, now we got to think a little bit more. 2 to what power equals 0? Well, we know that 2 to the 0 power equals 1. So we know that this is not possible. Because 2 to the 0 equals 1, x can't be 0. 2 to the negative 1 equals 1/2. So it's not possible to have an exponent, a value for x in this case, cause that left side to equal 0. So that left side doesn't work, but we do still have a second half of this equation. We can solve this one. X squared equals 9/4. Square root, don't forget it is plus or minus 3/2. So last one here, number 18. Go ahead and try this one on your own. Pause the video before you do, and then once you're done trying it, then you can go ahead and unpause it, check your answer, and we'll be good. So checking out number 18, it is very similar to the last one. There is a GCF of 3 to the x, which is what we factored out first. After we factored out, again, we already talked on the last one, there's no x value that can be plugged in to get 3 to the x equal to 0. So that does not have a solution on the left side there. But then on the right side, we're left with a nice quadratic quadratic because it does factor. And after you factor it, solve for each factor, and you get x equals 3/2 and x equals 1. So tonight on your homework, again, you're probably going to be graphing some with calculator and without a calculator. Please make sure that you do the ones without a calculator when they ask you to do them without a calculator. And then you're going to be solving some equations and using those exponent properties. If you have questions, please reach out to your teacher, and good luck with the homework.